All right. Good morning. Just going back to inequalities, and we were looking at inequalities involving polynomials, and then crossing over to the threshold of looking at rational inequalities. And I just want to kind of break down in terms of the mechanics some of the items we have regarding the graphing features, uh, this particular rational function, as well as the how this ratio compares to 0 in its various capacities, like less than or equal to, greater than, as well as greater than or equal to. And now, say for r of x equal to x squared plus 5x plus 4 all over x squared minus 2x minus 3. Say if I'm looking for the domain, again, for r of x to be defined, okay, the denominator cannot be equal to 0. Okay, so you have x squared minus 2x minus 3 cannot be equal to 0 in order for r of x to be defined. Okay, so we're going to have here, upon factoring, in case you have x plus 1 times x minus 3 cannot be equal to 0. And so for what will be excluded from x will be those values that would set x plus 1 and x minus 3 to 0. And if x plus 1 cannot be 0, well, we have that x cannot be equal to negative 1. And if x minus 3 cannot equal 0, well, we have that x cannot be equal to 3. And for what we have in the case of the domain of this rational function, okay, so we have starting from negative infinity, and then we have approaching but not including the smaller or smallest of the restricted values, so we have negative 1. Again, we have parentheses, and then we have going past negative 1, approaching, and not including 3. Again, we have bypassing 3, and we have for the rest of the domain, we have those values of x greater than 3. And in terms of what we have regarding asymptotes, okay, and in the case of vertical asymptotes, again, they will be obtained by restrictions from the domain whose factors will still be around after the function is reduced to lowest terms. Okay, so we have with x squared plus 5x plus 4. Okay, so again, this will factor out to x plus 4 times x plus 1. And we're going to have all over, okay, we have the quantity of x plus 1 times that of x minus 3. And if you notice, we have x plus 1 common to both the numerator and denominator. So x plus 1 completely cancels. And because x plus 1 cancels out, that means that the restricted value originating from this will be a location of a hole in the graph. Okay, so we have a hole at x is equal to negative 1. And for what we have in following through, okay, so you have from the numerator left over. Okay, so I have x plus 4. Again, this is going to be all over x minus 3. Okay, so x minus 3 remains. And since it does remain, okay, this means that the restricted value of 3 Okay, this will define the only vertical asymptote of this rational function. Okay, so we have that x is equal to 3. All right, now in terms of any other asymptotes, and this will come down to comparing the degrees of the numerator and denominator. Okay, so we have, once again, so we have in the numerator, okay, the highest order term is x squared. Okay, so we have that n is equal to 2, and in the denominator, we have x squared is the highest order term, and so we have the degree m is also at 2. So we have in comparing, okay, and it's going to turn out that n is equal to m. And once again, if the degree n is less than m, or if it is equal to m, there will be a horizontal asymptote. And with the degrees being the same, we have a horizontal asymptote, and this will be y is equal to the constant that results from taking the highest order terms in the numerator and denominator. So from the numerator we have x squared, and the denominator, again, we have x squared. And x squared over x squared is going to go to 1. All right, so in terms of what we have in sizing things up, so for what we have right now, for the graph of the function, okay, so you have r of x, or y, is equal to x squared plus 5x plus 4 all over x squared minus 2x minus 3. So you have these curves in blue, and for the dashed vertical and horizontal lines, okay, those are going to be the asymptotes. So for that running up and down, that is the vertical asymptote, x is equal to 3. And that running horizontally, okay, that would be the horizontal asymptote, y is equal to 1. And once again, okay, if you notice, we have this open circle, and this again signifies, okay, that there is a hole at x is equal to -1. All right, so this is what we have in the general framework. Now, taking what we have for r of x, now looking at solving for r of x in terms of what possible values there will be among setting it in various ways in terms of how it's going to compare to 0. Okay, again, so we have with r of x, you have x squared plus 5x plus 4 over x squared minus 2x minus 3. And again, just drawing out the factored form. And this is so as to be able to establish the zeros in order to set up the interval table so as to identify how r of x is going to compare to 0. Okay, so for what we have here, out of our factors from r of x, okay, so if I set x plus 4 equal to 0, okay, we have that x is equal to -4. And then we have with the binomial x plus 1. If I set this equal to 0, okay, so I have that x is equal to -1. And if I set x minus 3 equal to 0, okay, so you're going to have that x is equal to 3. All right, and just looking at what we have in terms of setting up a table of intervals. Okay, so this is our function r of x. Now for the zeros. Okay, first of all, we have -4. And -4, now this stems from x plus 4. And x plus 4 is in the numerator. And you can have a 0 in the numerator as long as you do not have a 0 in the denominator. So you're going to have for -4, okay, now this one, okay, that is going to be in the domain. For -1, now this stems from x plus 1. Now this is in the numerator. And had x plus 1 been in the numerator exclusively and not in the denominator, -1 would also be in the domain. But since x plus 1 is also situated in the denominator, -1 is not in the domain. And we have with x equal to 3. Again, this comes from the denominator factor x minus 3. So if x is equal to 3, well, instead of r of x being equal to 0, as it would be in the case of x equal to -4, okay, we would have a 0 denominator, and r of x would be undefined. And so like -1, okay, 3 is not in the domain. I'm just going to say NITD for not in the domain. Okay, so looking at setting up the table, okay, and again, this will be situated about these zeros. Okay, so you have for the first interval, so we have going from -infinity, approaching but not including -4. Then we have bypassing -4 and then approaching but not including -1. And then we have going past -1, approaching but not including 3. And then we finally have, for the last interval section, okay, we have those values of x which will be higher than 3. Okay, so looking at separating the interval sections. Okay, so if we're looking at supplying test values x, okay, first of all, we can select anything that is less than -4. So it's going to be a number that is more negative than -4. We can go with -5. Then we have anything between -4 and -1. You could go with either -3 or -2 if you go with integers. And we have between -1 and 3. You can choose 0, 1, or 2. We'll just go with 0 on this one. And then anything greater than 3. 4 is an option. And for what we have in terms of the value of the function r of x, okay. Now let's give you the breakdown for each of these. Okay, so you have for r of -5. Okay, so we have in the ratio. Okay, so you have x squared. We have at the square of -5. Plus 5 times -5 plus 4 and we have all over the square of -5 minus 2 times -5 minus 3 Okay, so just for the breakdown, so the square of -5. Notice I don't have a negative sign in front of the x squared, so I'm squaring all of -5. So that'll be 25. 5 times -5 is -25. And we have plus 4. And again, the square of -5 is going to be positive 25. -2 times -5, that would be a positive 10. We have minus 3. Okay, so for what we have here, 25 minus 25 goes out, and we have plus 4. 25 plus 10 is 35 minus 3 is going to be 32. And just for the reduction, okay, this will become positive 1/8. Now for what we have in the case of r of -2, so just kind of running it through the process. So you have the square of -2 plus 5 times -2 plus 4 and we have all over the square of -2 minus 2 times -2 minus 3. Okay, so square of -2 is 4. 5 times -2 is -10. And we have plus 4. Okay, so you got the square of -2 is 4. -2 times -2 is another positive 4. Then we have minus 3. Okay, so we have 4 minus 10 is -6 plus 4. This will be -2. And we have 4 plus 4 is 8 minus 3 is 5. So we're already going to have the simplified form whereupon r of -2 is equal to minus 2/5. Now for r of 0, okay, the variable terms will become negligible, and so for what is going to be left over will be the constants, positive 4, negative 3. So r of 0 is going to be it's going to be equal to minus 4/3. And for what we have in the case of r of 4, okay, so we have 4 squared plus 5 times 4 plus 4 okay, and then we have all over 4 squared minus 2 times 4 minus 3. So you got 4 squared is 16. 5 times 4 is 20. Plus 4. Okay, so you got 4 squared is 16. You have minus 8 minus 3. Okay, so just clustering together. So you got 16 plus 20 plus 4, that will be 36 plus 4, so that will be 40. And we have 16 minus 8 is 8, minus 3 is 5. And we have 40 divided by 5. Okay, so this will come out to a positive 8. Okay, and in terms of what we have regarding the sign values, okay, so for the sign of r of x, okay, so we have anything plugged in for x that is less than negative 4, negative 5 being the sample. We have the output is going to be positive, like in the case of 1/8. Okay, so you have positive. So this will indicate that r of x is greater than 0. Anything we plug in between negative 4 and negative 1, okay, we have a negative output. So we're going to have the r of x is less than 0. Anything between negative 1 and 3 for x, okay, we're going to have another negative output. So we have the r of x is less than 0. And then anything higher than 3 that is plugged in, okay, the output is going to be positive. Okay, so we have the r of x is greater than 0. Now, in terms of our inequality situations, as r of x is compared to 0, okay, so r of x again, we are referencing this particular ratio. In fact, what I'll do here, okay, so this is what we got for r of x. Okay, now for r of x is less than 0, okay, we're going to have for the solution set, okay, so where r of x is less than 0, you have the middle two interval sections. Now, since the nature of the inequality is less than, there's no equal sign, so the grouping symbols in the interval solution will be parentheses, and parentheses only. Okay, so you have between negative 4 and negative 1. Then we have between negative 1 and 3. As for r of x is less than or equal to 0, Now again, less than or equal to 0 is in the same direction as r of x is less than 0. So we are still involving the same limit values. And with the equal sign involved, there may be, not guaranteed, but there might be a bracket. Okay, so just for the deciding factor now, -4, again, -4, whether that is going to be bracketed, that is going to be contingent upon whether -4 is in the domain. And since it is, it officially sets r of x equal to 0. And since -4 is in the domain, then we'll do a little color coding here. So in the domain, I had that written in blue, so I had this bracket in blue. As for -1 and 3, okay, both of those were restricted from the domain. -1 and 3 not in the domain. So just stressing and just putting in red. Okay, so both -1 and 3 will be in parentheses. So the red referencing not in the domain. Now for r of x is greater than 0, again, no equal sign, so we will have parentheses only. And for r of x is greater than 0, we're looking at the first and the last subinterval sections. So we're looking at values of x which should be less than -4, along with values of x, okay, that will be greater than 3. And then for r of x is greater than or equal to 0. Again, r of x, you have this ratio. Again, greater than or equal to 0 is in the same direction as greater than 0. And for the enclosures, okay, now, again, infinities are boundless. So the parentheses will be locked in around negative and positive infinity. And as for the finite values, -4 and 3, again, the equal sign indicates that we may have brackets, but again, not a guarantee. Now, -4, again, is in the domain. So you have a bracket to enclose -4. And as for 3 is not in the domain. And so we're going to have a parenthesis. So those would be your respective inequality problems and corresponding interval solutions. And now, let me just kind of reference the table, and also just make a mention. See where I want to fit this. I just wanted to mention, when we looked at the graph of the rational function and the asymptotes, and again, there was a hole at x equal to -1, and you still have that scenario again. So you still have the curves in blue, and you got the asymptotes, x equal to 3, y is equal to 1. And I just wanted to mention, like, whenever we tested out -5, okay, the corresponding y value was at 1/8. So you got -5 and 1/8, and the decimal form is going to be 0.125. And when we tested out the value of -2, the output was at -2/5. So you got -2 and -4/10, or -0.4, and that's the decimal equivalent of -2/5. And again, we have, whenever x was at 0, again you have -1.333, and that is in reference to -4/3. And then for x is equal to 4, again the corresponding function value was at 8, so you got 4/8. And so you have these 4 points, okay, to originate from these particular tested values in x and the corresponding rational function values. Okay, and so if you notice, okay, we have the function values, the sign values, all that, like using our tested values x and the corresponding y values. Those, again, are just elements that will make up the entirety of what we have in the graph of the rational function. All right, so I just wanted to add in those details. Okay, now in the case of looking at what we have regarding comparison inequalities. And we've already been comparing all along, but I'm eventually going to make, I'm going to maintain the course of comparing to 0, and then I'm just going to give you a case whereupon we'll have a comparison between ratios. Okay, and let's say that if you have a rational function, r of x is equal to 1 over 2x. Okay, and we have only one x expression. Okay, so that's just going to be 2x. We have 2x is equal to 0, so from this we have that x is equal to 0. And we have within the framework, okay, so I have r of x, again, is equal to 1 over 2x. Again, there's only one 0. And it's going to be the value of 0. And since this originated from 2x, which was in the denominator, it's going to turn out that the only 0 we have, instead of setting the rational function equal to 0, is going to cause it to become undefined. So 0 is going to be a restricted value. So this will not be in the domain. And just kind of a quick sampling, if I set up intervals about the 0, okay, so with this compact rational function, okay, it's going to be sort of binary in terms of the interval. Either the value x is going to be less than 0, or it will be greater than 0. So either it's going to be negative or it's going to be positive. Okay, so just looking at partitioning the interval sections. And for what we have in the case of the tested values x, we say anything less than 0 will go with -1. Anything greater than 0, we'll just go with the number 2. Just kind of create a different absolute value between the selections. And for r of x equal to 1 over 2x, okay. So we have for r of -1, you're looking at the reciprocal of 2 times -1, so 1 over -2, so this will become -1/2. in the case of what we have with r of 2, okay, so that's going to be 1 over 2 times 2. 2 times 2 is 4. Okay, so this will become positive 1/4. Okay, now for what we have in the case of the sign value of the ratio, okay, so for any value selected that is negative, it's going to turn out that the output is likewise going to be negative. So r of x is less than 0, and then anything selected that is positive, okay, we have the output is also going to be positive. Okay, so this is what we have, just going back to what we have in the setup. Now, if I set up inequalities revolved about r of x equal to 1 over 2x, okay, so if I have 1 over 2x is less than 0, and again, since r of x is equal to 1 over 2x, so I'm looking at where r of x is less than 0, so your solution sets will be the negative values for x. As for 1 over 2x is less than or equal to 0. Now again, you have in the same direction as where r of x is less than 0. So again, we are involving negative infinity and 0. Again, infinities are boundless. Now with the equal sign, there could have potentially been a bracket. However, our only 0 attained in the setup was 0, and that is not in the domain since the corresponding factor is in the denominator. So 0 is going to stay in the parentheses, again, not in the domain. And for 1 over 2x is greater than 0. So we are referencing where r of x is greater than 0. So we're looking at the outcome to be the positive values for x in the real number system. And for 1 over 2x is greater than or equal to 0. Again, we're looking at the same limits, and infinities are boundless. Okay, so that stays in the parentheses. And again, 0 could have been bracketed if 0 had been in the domain, and since it is not, we will maintain the use of the parentheses around 0. Okay, so if you notice, if you got equal signs in the inequality, it will stress the possibility but not the guarantee that there will be brackets. Okay, and so it turns out that the solutions to less than or equal to 0 turn out to be the same set of values, and likewise for greater than as well as greater than or equal to 0. Okay, so we have parentheses only throughout the interval solutions. All right, now let's say that if we have a rational expression, and we'll say that we have have r of x, okay, is equal to x minus 4 all over x plus 2. Okay. So you have r of x, you have x minus 4 all over x plus 2. So if I have x minus 4 is equal to 0, okay, we have that x is equal to 4. For x plus 2 is equal to 0. We have that x is equal to negative 2. So again, this is what we are using for r of x. And for what we have in the case of the zeros, okay, so you got 4, which originates from x minus 4, which is in the numerator. And again, you can have a 0 numerator as long as you do not have a 0 denominator. So x minus 4 is only in the numerator. Okay, so we can say that for what we have in the case of 4. Okay, so 4 is in the domain, or say ITD. As for negative 2, okay, this comes from x plus 2, which is situated in the denominator. And again, we cannot have a 0 denominator for the rational expression to be defined as a real value. So for negative 2, okay, that one is not in the domain. And if we set up a table of intervals, okay, revolved about these zeros, okay, so you have 4 and negative 2, and we have starting out, so you have going from negative infinity, approaching but not including the smaller of the zeros. In this case, we have negative 2, and then we have going past negative 2, approaching but not including 4, and then for the rest you have those values x greater than 4. Okay, and looking at the selection of test values for the input, okay, so for anything less than negative 2, we'll just go with negative 3. Between negative 2 and 4, we can go with 0. Anything greater than 4, 5 will do. And here we have r of x, okay, equal to x minus 4 over x plus 2 Okay, so in the case of r of negative 3, okay, so we've got negative 3 minus 4 over negative 3 plus 2, so we have negative 7 over negative 1. So we have a negative over negative, okay, becomes a positive. And in the case of what we have with r of 0, okay, so you have 0 minus 4 over 0 plus 2. So we'll have negative 4 halves, and that will reduce to negative 2. Now for R of 5, okay, we have in this one, okay, so you have 5 minus 4. All over 5 plus 2. Okay, and so then we have 5 minus 4 is 1. 5 plus 2 is 7. Okay, so this is already in simplified form, so the output, again, is going to be positive. Okay, so for the sign of R of x, okay, so for the first interval section, okay, the output is positive. So if R of x is greater than 0, then we have in the middle, have a negative output, so R of x is less than 0, and then we have for the last, okay, you have a positive. So you have the R of x is greater than 0, okay. And just looking at what we have among the possible comparison to 0 inequalities. Okay. There we go. Okay, so we have for a rational function, okay, so if I have x minus 4 over x plus 2, okay, is less than 0. Okay, so where R of x is less than 0, okay, we have for the solution set, okay, we have between negative 2 and 4. Again, no brackets due to the nature of the inequality. Now for x minus 4 over x plus 2 is less than or equal to 0. So we're still involving the same numbers. Okay, now the equal to sign, okay, we're going to be inclusive of those zeros in the domain. Okay, so if you notice, we have with negative 2, okay, again, negative 2 is not in the domain, so instead of setting equal to 0, it would set the rational function undefined. So negative 2 stays in the parenthesis. Now for 4, that is in the domain. So that'll be in the bracket. As for x minus 4 over x plus 2 is greater than 0. Okay, so you're looking at where R of x is greater than 0. So the interval sections will be inclusive of those values of x less than negative 2 and those values of x greater than 4. And for what we have seen in the scenario whereupon x minus 4 over x plus 2 is greater than or equal to 0, again, greater than or equal to 0 is in the same direction as R of x is greater than 0. So we're still involving, okay, the same quantities, okay. And once again, infinities are boundless, so we maintain the use of parentheses. And again, with the equal sign and looking at what is in the domain and what is not. Okay, so -2, not in the domain. So you have a parenthesis to enclose that, and for 4 is in the domain, and so this value can be bracketed. And again, these will be your corresponding interval solutions for the given inequalities as x minus 4 over x plus 2 is compared to 0. Now, just an item here. Now, the book doesn't seem to stress it quite so much, but in case of Alex happens to sneak in a problem, okay, that is a bit of a higher caliber in terms of the amount of work that is to be done. Say if you have a comparison between ratios. Okay, so if you're looking at solving for x, okay, so we have if you have 2 over x plus 2 is greater than or equal to 1 over x plus 4. Okay, now we're looking at solving for x such that 2 over x plus 2 is greater than or equal to 1 over x plus 4. Notice that we do not have a comparison to 0 inequality, but I can fix this. Okay, so if I have it where 0 is on the right just as it has been all along, I can just move 1 over x plus 4 by subtracting. So I'm going to have here, so I'm going to have, in this case, so I'm going to have 2 over x plus 2 minus 1 over x plus 4 is greater than or equal to 0. Now what I'm going to do here is that I'm going to consolidate the difference. And what I'm going to do here is sort of move to the side. Okay, so you have 2 over x plus 2 minus 1 over x plus 4. And if I make into a single ratio, okay, now I need to be able to work with the least common denominator. So this kind of goes back to the chapter R portion of combining fractions that do not share a common, that are unlike in the denominator. So you have unlike denominators, and so if I write both of these in terms of the least common denominator, so I have the least common denominator. Okay, so I have x plus 2 times x plus 4. And if I rewrite both of these ratios in terms of the least common denominator, okay, so I have 2 over x plus 2. Now I have the x plus 2 part of the LCD, but I'm missing the x plus 4. So I'm going to multiply the first ratio by 1 in terms of x plus 4 divided by itself. Then I have subtraction. Then I have 1 over x plus 4. Now, looking at what we have for the least common denominator, now we have already x plus 4, but missing x plus 2. So now we're going to multiply this second ratio by 1 in the form of x plus 2 divided by itself. And I'm eventually going to unite the ratios, but for what we have in the meantime, so you have x plus 2 times x plus 4. Okay, so if I distribute 2 over the quantity of x plus 4, so I'm going to have 2x plus 8. And it's going to have subtraction for now. And okay, got x plus 4 times x plus 2, and I can just switch the order. Now we got 1 times x plus 2, so we have x plus 2. Now we got the same denominator, okay, and as I combine the numerators, now all of x plus 2 is going to be affected by the subtraction in front. Okay, so we have from the first numerator, okay, so I have 2x plus 8, then we have subtracting, and this will affect not just x, but also the plus 2, okay. So as we look at narrowing it down, so we have 2x plus 8 minus x minus 2. Okay, we have all over the quantity of x plus 2 times that of x plus 4, and narrowing it down. So you got 2x minus x becomes x. 8 minus 2 is 6. Okay, we have x plus 6 all over x plus 2 quantity times the quantity of x plus 4. Okay, so for this difference as a consolidated ratio, notice we have in the outcome not 1, not 2, but 3 variable expressions. Okay, so you have what's going to become x plus 6 all over x plus 2 times x plus 4. Is greater than or equal to 0. Okay. Okay, so we have in the case of r of x, okay, so again you have x plus 6 and we have all over x plus 2 times the quantity of x plus 4. Okay, now for the zeros, now from x plus 6, okay, have x at negative 6. Okay, since x plus 6 is only in the numerator, the 0 from this is going to be in the domain. For x plus 2, okay, this is in the denominator, and the resulting 0 is negative 2. And negative 2 is not in the domain. Again, since x plus 2 is in the denominator. And then for the next 0, okay, that one is also not in the domain. So from x plus 4, I have negative 4. So we have not in the domain. And just setting up a table of intervals. Okay, so we have among these now negative 6 is the smallest. So the first section we have between negative infinity and negative 6. Then we have going past negative 6 and approaching but not including negative 4. And then we have going past negative 4 and approaching but not including negative 2. And since negative 2, in spite of being negative, ends up being the highest of the zeros we have for the rest of the set, we'll have those values of x greater than negative 2. And again, just setting up the partitions to separate the subintervals. Okay, so we have, in the case of tested values, just going back to the table. So for the test value x, so anything less than negative 6, okay, negative 7 is a possibility. And if I want to stick with integers, I can only apply negative 5 for the next. Also, only negative 3 for the third subinterval. And then anything greater than negative 2, I can just go with the number 0. And again, just for the function value for r of x, is equal to x plus 6 all over x plus 2 times the quantity of x plus 4. That's going to turn out that for r of negative 7, okay, if I plug in negative 7 for x, okay, it's going to turn out that for r of negative 7, and we have like negative 1 over negative 5 times negative 3, so this would be negative 1 over 15, so r of negative 7, okay, it's going to be minus 1/15. And in the case of r of negative 5, okay, you got negative 5 plus 6 is 1. And you got negative 5 plus 2 is negative 3. Negative 5 plus 4 is negative 1. And so you're going to have, in this case, you're going to have positive 1/3. And in the case of r of negative 3, okay, so right now we've got negative 3 plus 6 is positive 3. And we've got negative 3 plus 2. Okay, so you have negative 1. And we have negative 3 plus 4. Okay, that is going to be positive 1. So we got 3 over negative 1. So we have for this output, okay, that is going to land at negative 3. Now as for r of 0, okay, so we have 6, and 2 times 4 is 8, and 6/8 reduces to 3/4. And for what we have in the case of the sine of r of x, Okay, so for anything less than -6 that is selected for the input, okay, the output is going to be negative. So R of x is less than 0. And then we have for the second, the output is positive. So R of x is greater than 0. Then we have for the third, okay, we have a negative. So we have the R of x is less than 0. And then finally we have a positive, whereupon we have R of x is greater than 0. Okay, and so for what we have in the overall framework, okay, so and again, this is the inequality we started out with. And these were the conditions, okay, resulting as I converted this comparison inequality between ratios, okay, to one where we have comparison to 0. So again, you have starting out, you have 2 over x plus 2 is greater than or equal to 1 over x plus 4. Then converting to a comparison to 0 inequality. Again, this comes down to this ratio is greater than or equal to 0. So this is going to be stressing where R of x is greater than or equal to 0. And for what we're going to have in the case of the solution, okay, so you're looking at going in the same directions where R of x is greater than 0. So where we have greater than 0, okay, we're looking at involving the limits -6 and -4. And also have greater than 0, and you have involving the limits. Okay, so you have -2 and infinity. Now for the enclosures, now again you have the equal sign signaling the possibility of there being a bracket, but no guarantee, just like what we have with R of x equal to the reciprocal of 2x. So again, infinities are boundless, so infinity stays in the parenthesis. Okay, now as for what is going to be setting the expression equal to 0, and that will satisfy this original inequality throughout. So we have a -6. Now again, -6, that one is in the domain. So that means that -6 solidifies itself as being a solution. So that is going to be in the bracket. However, with -2 and -4, both as values that will not be in the domain, okay, those amounts will remain in the parentheses. Okay, so I have a parenthesis around -4 and also a parenthesis around -2. So this will be the interval solution of what we have for this particular comparison inequality. And again, there might be something about like this from Alex. And again, if you have a run-in with this, you want to convert as a comparison to 0 inequality. And I know that converting from this difference to a consolidated ratio, especially with all this work involved, it's about like pulling teeth. I get it. And there's a lot of work involved, and it can almost be like going into a forest and you venture out so far and you kind of forget how you got into the forest and how am I going to get out. Remember, okay, you just convert as a comparison to 0 inequality, and again, just consolidate the ratio, find out what zeros will be in the domain as well as those that will not be in the domain. And then you just set up your table about the zeros and just test out as we had with the polynomial inequalities.